In today's lecture, I want to talk about state machines. State machines can be very useful to write shorter and more concise contracts both on-chain and off-chain. And there's support for state machines in the Plutus libraries that is higher level and builds on top of the lower level mechanisms we have seen so far. As a running example for today, I want to implement a little game played between Alice and Bob. It's a bit like rock, paper, scissors, but even simpler because there are only two options. So Alice and Bob both have two options. They can either play 0 or 1. And if they played it while being physically in the same room, it would be played just like rock, paper, scissors. So at the same time, they raise their hand and there's one gesture for 0 and one gesture for 1. And depending on what they play, one of them wins. So if they both use the same gesture, both choose 0 or both choose 1, then Alice wins. And if the choices are different, then Bob wins. Now let's imagine that Alice and Bob can't meet in person, but they still want to play the game. So they decide to play it via mail. Email or snail mail, doesn't matter. Of course, we will later implement it on the blockchain using Plutus. But how could that work? So Alice can send a mail with her choice, let's say 0 to Bob. But this, of course, gives a very unfair advantage to Bob, because now he opens Alice's mail and sees she picked 0, and he can simply reply sending 1, and he wins. And of course, if Alice instead picks 1, Bob can simply choose 0. So Bob would always win, at least if he's unfair. So what can we do about that? And there's a very clever trick that's often used in cryptographic protocols, and that's about commit schemes. So the idea is that Alice doesn't reveal her choice to Bob, but she commits to it so that she later can't change her mind. And one way to make that work is using hash functions. I mean, hashes are all over the place in the blockchain world. I mean, we have seen that, for example, addresses, script addresses are just the hash of the Plutus core script. And we have seen lots of examples of using public key hashes and so on. And what hash functions are, they are so-called one-way functions. So it's difficult or impossible, given a hash, to reconstruct the original document or the original byte string that was hashed to this hash. So one way we could try to make this work is that instead of sending her choice to Bob, she instead sends the hash of her choice to Bob. So she sends the hash of 0, which is just some, I don't know, cryptic byte string. So now Bob sees this cryptic byte string and he has no idea whether Alice picked 0 or 1. So he maybe picks 0 and there's no need for him to use a hash. So he can just send the 0 in clear text. And so now Alice would have won, but maybe Bob doesn't believe her. So there's then one additional step that Alice has to send another message to Bob where she now sends her actual choice. And then what Bob has to do is he has to check whether hash of Alice's claimed choice is indeed the hash he received earlier. And if it is, then he knows that Alice is not lying and that she indeed picked 0 and that he lost. But if this hash doesn't match up, then he knows she's cheating or trying to cheat, and he would win. And of course, if Alice instead picked 1, that would work exactly the same, except that the hash would be different. So this sounds promising, but there's one big problem with this, because in this game there are only two choices, only 0 and 1. So there are only two possible hashes. They may look very cryptic to Bob the first time they play, but I mean, sooner or later he'll notice that that he always sees one of these two hashes, and then he knows which choice Alice made. And that's almost as bad as if she directly sent her choice out in the open. But what we can do here is that Alice doesn't simply send the hash of 0, but that she first concatenates 0 with some arbitrary byte string, so-called nonce, that she picks. So the way this would work is first Alice picks a nonce, some arbitrary text, and then she sends the hash of the nonce and her choice. For example, 0 to Bob, which is some other cryptic byte string. And now it's not always the same byte string if she picks 0, provided she always chooses some random unpredictable nonce. So Bob receives that, and then it proceeds as before. So he sends his choice, for example 0. And now in the third message, Alice has to not only reveal her original choice, but she has to send the nonce as well. So in this case, she would send the nonce and 0. And then Bob checks that hash of Alice's claimed nonce concatenated with 0 is indeed the hash he originally received. And if it is, he knows he lost, and if it is not, then he knows she tried to cheat him. So this works very nicely, and this is what we will try to implement in Plutus on Cardano. So first we'll use what we have seen so far, and then we'll see how by using state machines the code can be much clearer and much shorter. Now what will this look like? So first Alice opens the game by posting the hash of her nonce combined with the choice she makes to play. So we have the hash. Then if Bob plays along, he will post his own choice. So Bob will play. And now we have the hash and Bob's choice. Let's call it cBob. If at this point Alice realizes that she has won, depending on Bob's choice, she can reveal her secret and the game ends and she has won. Let's assume that when Alice plays and when Bob plays, they both put down a certain amount of money, and in this scenario where Alice has won, Alice gets Bob's claim and her own back. If, however, after Bob made his move, Alice sees that she has lost, there's no need actually for her to do anything because she has lost anyway. So after a certain deadline has been reached, and Alice just doesn't reply, and then Bob claims his win. And there's another option that we haven't considered. It could be that after Alice starts playing, Bob simply is not interested and doesn't reply. So in that case, there must be a way for Alice to get her own money back. And that's basically all the things that can happen. So the different stages of the game. It starts by Alice opening with the hash of the concatenation of her nonce and her move. Then if Bob doesn't reply, Alice gets her money back. If Bob does reply, he puts down his choice. And then there are two possibilities again. Alice realizes she has won and she needs to prove it to Bob by revealing, and she wins. Or she doesn't do anything, and after some time has passed, Bob can claim the win and he gets both Alice's and his own stake. So let's implement this in Plutus now. First, just using the techniques we already know about. So let's look at the implementation. It's in the module even odd. And if you're wondering about that name, it's just because if the sum of the two choices of the two numbers that the players pick is even, then the first player wins, and if it's odd, the second player wins. Which is the same as what I said earlier, that if they agree, the first player wins, and if they are different, the second player wins. And I called the first and second player first and second instead of Alice and Bob here. So the data type game is used as a parameter for the contract. So G first and G second are the two players identified by their public key hashes. G stake is an integer that denotes the number of loveless that are to be used as stake in the game by each player. And then there are two deadlines, play deadline and reveal deadline. So play deadline is by what time the second player has to make a move before the first player can claim back his stake. And the reveal deadline is in the case that the second player has made a move, how much time the first player has to claim victory by revealing his nonce. Finally, we have a token represented by its asset class, and this will be the same trick that I used last time for the Oracle. That will be an NFT, an arbitrary NFT used to identify the right instance of the UTXO that we are using. So the idea is again similar to what we did with the Oracle, to use the datum of a UTXO sitting at the address of this contract, the script address of this contract, to keep track of what has happened where we are in the game. Then the type game choice. So that's just the two moves the players can make, 0 or 1. And I derived equality in the normal Haskell sense and an OR instance, but unfortunately for the Plutus equivalence of eq and OR, that's not possible. And I need eq for Plutus eq, so I do that by hand in the usual way. So, I mean, 0 equals 0 and 1 equals 1, and all other combinations are not equal. And for this to work with template Haskell, you have to put this inlineable pragma there as well for the equals operation. And game datum is what I will use as state for the contract. And byte string is the hash that the first player submits. And maybe game choice is the move by the second player. It's a maybe because in the beginning the second player hasn't yet moved. So then it will be nothing, and once the second player has moved, it will be a just. And same thing, I also need Plutus equality for game datum. And just also the obvious one that two are equal if both components, the hash and the maybe game choice, are equal. Now we come to the redeemer, and for that I also implemented a custom type that I call game redeemer. And that corresponds to the transitions we saw in the diagram I drew just now. So play is when the second player moves, and as argument it has a game choice. So the second player can play 0 or 1. So that will be play 0 or play 1. Reveal is for the case when the first player has won and must prove that by revealing its nonce. So the byte string argument here will be the nonce. We don't need to also provide the move that the first player made, because he will only reveal in the case he has won, and we know what move makes him win. So that would be redundant, and therefore I left it. And finally, claim first and claim second. Claim first is in the case when the second player doesn't make a move, so the first player can claim back his stake. And claim second is for the case that the first player doesn't reveal because he knows he has lost, so the second player can get his winnings. Then same helper function I used last time that I think is for some reason missing from the Plutus libraries. So given a value, extract the number of lovelesses contained in it. And then similar, last time I had the Oracle datum function, and now I did the same for game datum. So given an output of a transaction and some way to, given a datum hash, maybe get the datum, give me a game datum. And it's the same as with the Oracle last time. So it's these three steps. First I try to get the datum hash from the output, which may fail. Secondly, I use the second argument function to turn this hash into a datum value. And lastly, I try to pass this datum as something of type game datum. So that's exactly what I did for the Oracle last time. Now we come to the core business logic in the make game validator function. The first argument here is the parameter of the game type that I just explained. The second and the third argument are somewhat of a nuisance, and I just need them due to the fact that, as we have already discussed on Discord, it's not possible to use string literals to get byte strings in Haskell that is compiled to Pluto's core. And I want string literals representing the 0 choice and the 1 choice. So this will just be the byte string with the digit 0 and the byte string with the digit 1. But because I can't use string literals, I pass them in as auxiliary arguments. We'll see how we pass them in later. Then the usual datum, redeemer, and context. Let's look at some helper functions first. So info as before, own input and own output also as before. So this should never fail because we are in the context of validating the usage of a UTXO. So there should always be an own input, the input we are presently validating. Own output, if we are in a case where we are not done yet, where the game isn't over, we want that there is a new UTXO carrying the NFT with the updated datum. So for that case, we'll use this own output function, and it checks all the outputs that go to the same address and only succeeds if there's exactly one such. Output datum makes use of this game datum function that we defined earlier, and given the case where we have exactly one output to the same script address, it gives us the datum, tries to give us the datum. And that could fail, or otherwise we return the datum. So check nonce is for the case that the first player has won and wants to prove it by revealing his nonce and then proving that the hash he submitted in the beginning of the game fits this nonce. So the first argument is the hash he submitted. The second argument is the nonce he now reveals. The third argument is the move that both players made. It's called cSecond here, move of the second player. But this function will only be involved or only be relevant in the case where the first player knows he has won, which is only the case when he made the same choice that the second player made. So I could just as well have called it C first in principle. And in order to do this check, I mean, how did the computation of the hash work? Well, I take the nonce and concatenate it with the choice. But the choice, of course, here is of some abstract data type game choice. But in order to concatenate with the nonce, I need it in byte string form. And the idea is I just use this B as 0 for the 0 choice and B as 1 for the 1 choice. So this is just this conversion. And I call the byte string C first. So cSecond is of type game choice, but C first is of type byte string. And if the choice was 0, I take the byte string representing 0. If it was 1, I take the byte string representing 1. Then to compute the hash, I take the nonce, concatenate it with this byte string, and apply the SHA-256 hash function to it. So this is the hash that I get giving this nonce, and then the check is to make sure that that is indeed the hash the first player committed in the first place. And finally, I haven't mentioned that before, but we now have this state token, this NFT that identifies the correct UTXO. And the question is what happens to this NFT after the game is over and there is no UTXO at the game address anymore. And the way I've implemented now, I want it to go back to the first player. The first player needs to have it in the beginning in order to kick off the game and put the NFT into the correct UTXO. So I think it's only reasonable to give it back to him in the end, no matter who won the game. So this just checks, there's a function called value paid to and gets the context or the info from the context and pub key hash, and then it basically adds up all the values that go to that pub key hash in some output of the transaction. So I want that, so this just means that the first player gets the token. So now we can look at the conditions. There is one condition that applies to all cases simultaneously, and that is that the input I'm validating must be identified by the state token. So that's what I'm checking here, that the own input, the input I'm presently validating, contains the state token. And then what the rules after that depend on the situation I'm in. The first situation is the one where the first player has moved, the second player is moving now. So this is the transaction where the second player moves and chooses the move C. So the datum, the second component, must be nothing. Remember, that just means that the second player hasn't moved, so is moving now. And in this case, what do I have to check? I have to check that this move is indeed made by the second player, so he has to sign the transaction. This checks that the first player has put down the stake for the game. Then this checks that now in this transaction the second player adds his own stake. So in the output we now have twice the G stake game. Then we know exactly what the datum of the output must be. It must be the same hash as before, but now the nothing is replaced by just C, where C is exactly the move the second player is making. Then the move has to happen before the first deadline. That's exactly the point of this first deadline, the play deadline. Until then, the move must have happened. And finally, the NFT must be passed on to the new UTXO to identify that again. Okay, the second situation is both players have moved and the first player discovers that he has won. So in order to prove that and get the winnings, he has to reveal his nonce. So in that case, it has to be signed by the first player. The nonce must indeed agree with the hash he submitted earlier. He must do this before the reveal deadline. The input must contain the stake of both players. And finally, what I just said, the NFT must go back to the first player. First case is second player hasn't moved yet and also doesn't move in the deadline, so the first player wants his stake back. So this must be signed by the first player. It must only happen after the deadline has passed. The first player has provided his stake and he must get the NFT back. And the last case is both players have moved, but the first player has realized that he didn't win and therefore didn't reveal his nonce, or he got disconnected or whatever. In any case, he missed the deadline. So in that case, the second player wins, but the second player must sign this transaction. It must happen before the deadline. So there's a typo. So it must not happen before the deadline. He can only do that once the reveal deadline has passed to give the first player enough time to reveal the nonce if the first player won. We check again that the input, the consumed UTXO, has the correct stake. So in this case, both players must have provided their stake. And even though the second player has won and gets the money, the NFT must go back to the first player. And that's all legitimate transitions we can have. So in all other cases, we don't validate, we fail validation. So now let's look at the rest of the on-chain code. As always, we define this helper type that just bundles the information about what the datum and what the redeemer type are. Here we define the byte strings we're actually going to use for the two choices, 0 and 1. This is completely arbitrary. I could pick any two byte strings there. Game instance that compiles the code as before. So it's parameterized now by game and these two byte strings. This make validator function, so I have to apply all of them. But I just use these constants here. So now I only left with this one game parameter, as one would expect. And the usual boilerplate for validator and edges. Now, as preparation for the on-chain code, for the off-chain code, we will always need to find the right UTXO, so the one that carries the NFT. So I write this helper function find game output that gets the game, and then in the contract monad tries to find the UTXO. So it could fail, the UTXO could not be there, so therefore maybe. And then I return the usual things, the reference and the output itself. and additionally the game datum. And that's quite straightforward to implement. So first I get all the UTXOs at the game address. Then I use this find function. This is in data.list. And it's more general. It doesn't only work for lists, it works for more general containers of type T, but you can think lists. So it gets a predicate on elements and a list of A's and returns a maybe A. And the logic is if it finds an element in the list that satisfies the predicate, it will return it as a just, and otherwise it will return nothing. So if we do find even 1, 3, 5, 8, 11, 12, it will pick the first even number from the list, just 8. But if I remove the even element, then it will return nothing. So using this find, after we have all the UTXOs, turn them into a list of pairs. Then as F, we take such a pair, ignore the reference, just take the O, and check whether this output contains our token. So this line, which by the way happens in the maybe monad, will, if it exists, find us the UTXO that contains the token. And then we use the earlier defined helper function game datum to get the datum to this UTXO and return the triple. Okay, so now we have two contracts for the two players. One for the first player to play the game, the other one for the second player. The second player plays the game. And with corresponding parameters, first params and second params. So first params, we don't need the first player. The first player will be the owner of the wallet that invokes this contract, but we need the second and the other things we need to define the game, the stake, the two deadlines. Then we need the nonce that the first player wants to use to conceal his choice. And then the NFT, which we split into currency symbol and token name. And finally, the choice, the move that the player wants to make. So in this contract, first get our own public key hash. Then we can define the value of the game type. So we put our own public key hash as first player and then use the parameters we got from the first params. And for the token, we just assemble the currency symbol and token name into an asset class. Then this V value is just our stake that we must put into the UTXO plus the NFT that we must put into the UTXO. C is our choice. Now we compute the hash that we must put there, our commitment to our choice. So we take the nonce and concatenate it with, well, if we want to play 0, this 0-byte string, and otherwise the 1-byte string, and hash the result. The constraints for the transaction are very simple. All we have to do is we must produce a script output at this address with the datum that contains the hash we just computed. Nothing for the second player because obviously the second player hasn't played yet, and the value we computed. And we wait for transaction and log a message. So now the second player has a chance to move, but it must happen before this play deadline. So what we do now as first player is we wait until this deadline has passed. And then there are several cases. So we check whether we find UTXO containing the NFT. If we don't find it, then something has gone very wrong that can't actually happen because this can't just disappear. We know we just produced the UTXO at this address, and all anybody else, the second player can do is make a move, but that doesn't destroy the UTXO. I mean, it removes the UTXO but produces a new one at the same address again. So we should find it. There's no way we cannot find it. But nevertheless, if that happens, then I'm throwing an exception. But normally we will find it. So we have this triple, turning the UTXO and the datum. And in this case, the second player hasn't moved. So the deadline has passed, the second player hasn't moved. So what we can do is we can invoke this claim first redeemer to get our stake back. So as constraints, we just say we must spend this UTXO we found with this redeemer. And as lookups, we need to provide the UTXO and we must provide the validator of the game. And in that case, we log that we reclaimed the stake. Second case is that the second player did move, and there are then in turn again two cases, that the second player moved and won, or that the second player moved and lost. So this is the case where the second player chose the same move that we played, so we won. And in the other case, the second player won, and we can't do anything, so we just don't do anything. But if we won, we must now reveal our nonce to get the winning. So we use the reveal nonce redeemer. And we must also submit this transaction before the deadline for revealing has passed. And we again need lookups. We again need to specify the UTXO, and we must provide the game validator. And then we submit and wait and have won. Now for the second player, the parameters are very similar. Except that now we don't need to provide the second player because that's us, but the first player, stake, and the two deadlines as before, currency symbol and token name for the NFT as before, and the choice, the move we want to make. We don't need the nonce now because the nonce was only for the first player. Okay, so we start by looking up our own public key hash and can then define the game value, similar to as what we did for the first player. And now we try to find the UTXO that contains the NFT. So if we find it, and so BS is the commitment of the first player, the hash, and nothing because we haven't moved yet. So in that case, so we found the game. So this is the most interesting case, but let's look at the second case that it's not like that. Well, in that case, we just didn't find a game where we can move, so we can't do anything. So it's enough to concentrate on this case. So we found the game, and now we want to make our move, so invoke the play redeemer. So token is the NFT. Now V is the value that we must put in the new output. Remember, if we do the play transaction, we must consume the existing UTXO and produce a new one at the same address. And the old one should contain the stake that the first player put in, and now we must add our own stake, and we must keep the NFT in there. And the NFT, of course, is also contained in on the input side already. So what we must put in the output is, so X is just local variable here so that's the stake in Loveless. So we must into the output put twice the stake and the NFT. C is our choice. Let's look at the constraints first. So we must spend the existing UTXO with redeemer play, our choice. Then we must create a new UTXO with the updated datum. So same BS, but now just C, just our move. And this V we computed, which now also contains our own stake in addition to the first player's stake and the NFT. And we must do this before the deadline passes to make the play move. And we need lookups, so we must provide the UTXO. And because we are consuming the script output, we need the validator. And because we are producing one, we need the script instance. Then we do the usual thing. So we submit, we wait for confirmation, we log. Now it's the first player's turn again. So we wait until this reveal deadline has passed. And we again try to find the UTXO, which will now or could now be a different one. That's why I call it M prime. So if we don't find an UTXO anymore, that means that in the meantime, while we were waiting, the first player revealed and won. So in that case, we have lost, we can't do anything. If we still do find the UTXO, it means the first player didn't reveal, which means either the first player left the game for whatever reason, or he lost and couldn't reveal. In any case, now we can claim the winning. So we must spend the UTXO we found. We must do this before and after the reveal deadline has passed, because until then the first player still would have time to make his revelation. And we must hand back the NFT to the first player. And as lookups, we again need this UTXO, and we must provide the validator. And we do the usual thing and log the message. And that's it. That's the two on-chain contracts. But now to make them more accessible, we define schema, game schema, which has the usual blockchain actions, and two endpoints, one for the first player taking the first params, one for the second player taking the second params. And we define a contract called endpoints that offers the choice between these two endpoints. And no matter what is chosen, after that is then run, it recursively again offers this choice. And first and second is simply our first game and second game, where we first block and wait for user input, for external input to provide the parameters, and then bind the contracts we defined earlier. And that concludes the first version of the game that doesn't use state machines. Now let's test this using the emulator trace monad. So the code is in module test. And let's first look at the test prime function, which is parameterized by two game choices. So the idea is that we'll run or simulate a game where the first player makes this choice and the second player makes that choice. And then in the test function, I just run all four combinations in sequence. And as before with the Oracle, I'm using this run emulator trace IO prime variant because I want to specify an initial distribution. And I just want to provide wallet 1 with this NFT. So I just make up a currency symbol and some token name. I call it state token. And of course, in a real scenario, in a production code, we would have to generate this NFT. For example, using this forge contract from the currency use case, or also using our own contract that we discussed when we introduced minting policies. But NFTs are now not the focus of this lecture, so I just use this feature that I can conjure one out of thin air in this emulator trace configuration. Okay, so now let's look at the trace. So it takes these two parameters, the two choices C1 and C2. I just log some information that later in the output it's easier to identify what was going on. And I start two instances of the endpoints contract, one for wallet 1, one for wallet 2, H1 and H2. Look up the two public key hashes of the two wallets. And now I define the parameters that they will use. So first player is first wallet, second player is the second wallet. Stake is 5 ADA. Deadline, the first deadline is after 5 slots, the second deadline after 10 slots. This, of course, should be some random string in reality, but now I just fix one secret nonce. And I use this token that I provided earlier as the NFT. And of course, the choice of the first player is this C1 parameter from here, and the choice of the second player is C2. Okay, and with these definitions, very simple. I just call the H1, the first endpoint on wallet 1 with these FP parameters. I just wait 3 slots, and then I call the second endpoint for wallet 2 with the SP parameters that I defined here, and wait another 10 slots. So by that time, we should be in slot 13 or something. So both deadlines should have been passed, and there should have been enough time for everything to settle. And if we run this, so if we invoke, so I'm in module test now, and if I invoke this test, then let's go through the output. So the first scenario is that both play 0, so the first wallet should win. So here the first wallet creates the initial UTXO with its stake and logs this message that it made the move. Now the first wallet is waiting. Now the second wallet kicks in, looks for this UTXO, finds it, and sees that it can make a move. So it makes its move 0. And now the first wallet sees this move and realizes that it has won because both have played the same move. So now the first wallet must reveal, and does that here, and has 1. So the first wallet has 1. And we see in the final balances that wallet 1 does indeed have the state token back, this NFT, and now has almost 5 ADA more than it started with. The difference is, of course, due to transaction fees. And the second wallet has a bit more than 5 ADA less than in the beginning. So wallet 1 won. So now the second case is wallet 1 again plays 0, but wallet 2 plays 1. So the beginning is the same. So the first wallet creates this initial UTXO. Now the second wallet again finds the game and makes its move, but now the move is 1. So now the first wallet realizes that it has lost and doesn't do anything. So the second wallet detects that the first wallet hasn't made a move, and now invokes this claim second endpoint to get the money. So now if we look at the final balances, situation is reversed. Again, wallet 1 got the stake token back, but now wallet 1 has 5 ADA less and wallet 2 has 5 ADA more than before. And the other two cases are more or less the same, just the other way around. So if it's 1-0, then wallet 2 will win again, and if it's 1-1, then wallet 1 will win again. So this all seems to work as expected. So what is a state machine? The state machine, first of all, normally it has nothing to do with blockchain in particular. So it's just some sort of system. You start in a certain state, and then there are one or more transitions to other states. And so you can transition from the initial state into this one or that one, and that goes on. So basically it's just a directed graph. And then there may also be some states that are special in that they are so-called final states, from which there are no possible ways out anymore, no transitions that lead out of the final state. And what does that have to do with blockchain and with our examples? So if we look again at the diagram we had earlier for how our game works, then we can consider that a state machine. So the initial state would be this one here, where the first player has made the move, and the state is basically characterized by this datum, by the hash. And in this state, there are two possible transitions. One where the second player plays, Bob plays, and the second one where it doesn't play and the first player can reclaim. So all the nodes in this diagram correspond to states, and all the arrows, the edges of the graph, correspond to transitions. And in particular in the blockchain, the state machine will be represented by a UTXO sitting at the state machine script address. And the state of the state machine will be the datum of that UTXO. And the transition will be a transaction that consumes the current state, this current UTXO, using a redeemer that characterizes the transition, and then produces a new UTXO at the same address, where the datum now reflects the new state. So that's the relation. And that fits a lot of situations very nicely. And there is special support in the Plutus libraries to easily implement such state machines. And we will see when we use this approach that our code will be much shorter. The support for state machines is in package Plutus contract in the module Plutus contract state machine. And let's first look at what a state machine is. So a state machine has two type parameters, S and I. That stands for state and input, and that corresponds to datum and redeemer. So in the actual implementation and the manifestation of the state machine on the blockchain, S will be the datum type and I will be the redeemer type. And so a state machine is a record type with 4 fields. So the most important one probably is the transition that defines from which states, using which transition, you can change into another state. And this state S type is defined here. So that is basically the datum, the state itself, and also the value. Remember I said that this will be represented, the state machine will be represented by a UTXO, so the state of the state machine is a UTXO, and that has a datum and a value. So we have access to both in this state type. So given the state type, so the present datum and value of the UTXO, and a transaction that tries to consume this UTXO with the redeemer I, we can indicate that this transition is not allowed by returning nothing in this function. And if it is allowed, we return a tuple, and the second component is the new state. So this transaction will consume the existing UTXO and produce a new one at the same address, and this here will be the new datum and value of the new output, the new UTXO. And then we can have TX constraints that until now we've only seen in off-chain code that specify additional constraints that the transaction that does this transition must satisfy. So that's the transition function. Then we have a function, just a predicate on datums, basically on states, that tells us whether it's a final state or not. So final states are special in that in this transition function, if we transition into a final state, then there mustn't be any value attached with it. And then this output that normally gets produced, so we normally consume the UTXO representing the old state and produce a new output representing the new state. But if this new state is final, then we don't. So then we don't produce a new UTXO. So basically the machine ends there, it stops. So that's this SM final. SM check is very similar to this transition function, except it doesn't have the value. So it just gets the datum and the redeemer and the context and returns the bool. So this is basically an additional checks that can't be expressed in terms of these TX constraints. And finally, we have maybe an asset class. So often you have the problem that you must identify the right UTXO. If there are several UTXOs sitting at the address of the state machine, which one is representing the current state? And as with the Oracle and also in the contract we saw just now, the most common trick to use is to have an NFT identifying the right one. So if we have this NFT, then just the asset class of that NFT would be specified here. But you can also put nothing there and use some other mechanism to identify the right UTXO. I have implemented the same game now using the state machine approach in module state machine. So the beginning is exactly the same. So the game parameter, the game type is exactly the same. Game choice is the same. This is all the same. Game datum has slightly changed because I have added a second constructor that are called finished that we didn't need before, and that is supposed to represent the final state of our state machine. So it won't correspond to a UTXO, but we need that for the state machine mechanism to work. So the first constructor is as before, hash provided by the second player may be, hash provided by the first player may be made by the second player, and then this additional constructor to represent the final state that the game has ended. That makes the definition of equality slightly more complicated because now I have to take this second constructor into account as well. But nothing serious going on there. The redeemer is exactly the same as before. These two helper functions are exactly the same as before. And now this is now the transition function of the state machine, which sort of corresponds, as we will see in a moment, to the make game validator that we had earlier. So this is basically the core business logic. And so it takes the game, the parameter, and now, as we saw in the definition of state machine, state datum. So remember that's a pair basically consisting of the datum and the value and the redeemer, and then we must return nothing if it's not allowed, and just a pair of new state and constraints on the transaction. Now let's try to compare the transition function of the state machine to the make game validator function of our first version of the game. So the first thing, I mean, of course the signature is different, but in spirit it's a very similar thing. So in both functions try to determine whether basically a combination of datum and redeemer and transaction is valid or not. So we will see the correspondence now. The first difference we notice is here in our old version, we first had to check that the input we are consuming, the UTXO we are consuming, actually carries the NFT. And that is missing in the state machine formulation because the state machine mechanism automatically takes care of that if we set this last field in the state machine to some NFT asset class. Then the mechanism will automatically check that the NFT is present in the consumed UTXO and also in the newly created UTXO, if it's not a final state. So let's look at this first case where the first player had moved. So the component for the second player was still nothing, and now the second player wants to make a play with choice C. So we check these 6 conditions here, and let's see how they are reflected in the state machine formulation. And in the state machine, we have this this state S, which remember is a combination of datum and value, and you can access those two with state value and state data. So state value S is now the value in the UTXO that we are consuming. State data S is the datum, and R is the redeemer. So we have this triple. And here I check that the value is actually the stake of the game. So the value contained in the consumed UTXO. And that's the condition that was the second condition that we checked here. Now the result of the transition function, recall, if it's valid, it's just a pair. And the first component of the pair is constraints on the transaction, formulated using this constraints module that we know from off-chain code. And the second component of the pair is the new state of the resulting UTXO, which again is given by datum and value. So here we are specifying with this transition, if the second player makes a move, the new datum will be BS just C, and the new value will be twice the stake of the game, because it's now the first player stake and the second player stake. We leave the NFT out of here, even though it should be present in the UTXO, and that is again because the state machine implicitly takes care of that NFT, that it's passed through, so we don't mention it here. So this here corresponds in the old one to this check, that the datum is BS just C, and that the value is right. This is this one here. And we don't need the last check, as I said. Here we check that the output again contains the NFT. We don't need that because the state machine does that automatically. So now what is missing? So here we have these 2 constraints, must be signed by second and must validate N before the play deadline. And this corresponds here to the first condition, must be signed by the second player, and the deadline thing is here. And if you check exactly all these conditions are covered here as well in slightly different form and actually shorter form. And we don't have to worry about the NFT, that already makes it shorter. Now let's look at the second interesting case where the second player has played and the first player sees that he has won. So now the first player has to reveal. So in the old version we check it's signed by the first player. This is here. Then we check the nonce. That is nowhere here. And the reason is that that condition can't be expressed in terms of a constraint. And that is exactly what this other component of the record type of the state machine is for, the check function. So we will see that in a bit. So this is missing for now. We don't have this nonce check. Then the deadline check is here. This just checks that the input value is right. So we have that here on the left-hand side. And finally, we check that because the game is over, the NFT should go back to the first player. So that the game is over, we specify here by specifying the finished state and saying that no money is left in the contract. And here we say that the NFT must go back to the first player by using this must pay to pubkey first player token. Token is the only helper function I define here in the transition function. That's just the NFT. Now the third interesting case is where the second player doesn't play, so the first player reclaims. So in the old version we checked it was signed by the first player. It happened after the play deadline had passed. The input was correct, and the NFT goes back to the first player. And this is exactly here as well. Must be signed by the first player. Deadline must have passed. The NFT must go back to the first player. Here on the left hand side here we have that the value must be right that we consume. And finally the game is over and nothing is left in the contract. And then the last case where the first player has played, the second player has responded, and the first player realizes that he has lost and doesn't respond anymore, and the second player now wants to claim the winning. So must be signed by the second player. That is here. Reveal deadline must have passed. That's here. The value must be correct. That's here on the left hand side. And NFT must go back to the first player. That's here. And the game has ended and no money is left in the contract. And all other transitions, so all other states with arbitrary transitions are invalid, and we indicate that by returning nothing in this function. And we see the conditions themselves are maybe not much shorter than they were in the old version, but we only need this tiny helper function here, this token function, and not this own input, own output stuff. That's all handled by the state machine mechanism. And we don't have to worry about the NFT. But we are not done yet defining the state machine. There were other fields in the record. One is final, so we must specify what final states are, and that's just this finished state. So final finished is true and everything else is false. Then we left out the nonce check in the transition function because we couldn't express that as a constraint. And that's exactly what this check function is for. We have two auxiliary arguments, these two byte strings that we also had in the other version, 0 and 1, for the same reason we need that here. And then datum and redeemer and context, and must just return whether this additional check is satisfied. We ignore the context, we don't need it here. And the only condition we have to put into this check function is the one with the nonce, and that was in the situation where the second player had played, just C, and where the redeemer is reveal nonce. And this line here is just the old check we had in the first version as well. We compute the concatenation of the nonce and the byte string corresponding to the move, hash that, and compare it with the originally provided hash. And all other situations we don't need an additional check and therefore can return true. Now we can define our state machine, and so for now it has these three parameters, the game and these two auxiliary byte strings, and it returns a state machine. And we just provide the four fields that we just defined. So transition game, that was the important one, and this final check, the additional check, and finally the thread token, which we just take from the game value. Now there is machinery provided by the state machine to make a game validator. So what our old make game validator function can now be replaced by using the state machine and using the make validator game state machine. So game state machine is our state machine here, and there's a make validator function that turns that into something of this type, which is exactly the type we had before in our handwritten version. So this is similar to before. I mean, we had this other mechanism to bundle datum type and redeemer type. The state machine does the same basically. So now our type gaming can just be state machine game datum game redeemer, our two strings. And now I provided a second version of game state machine where we only have to specify the game and not these two strings. And that won't work in on-chain code, so it doesn't have this inlineable pragma because of the literal strings here. But in off-chain code, it works perfectly fine, and then we don't have to provide these two additional parameters. Now this is exactly as before, so the same boilerplate we had before, except now this make game validator has been defined here using the state machine mechanism instead of doing it explicitly. And game address, game client, no, game address is the same. Game client is a new thing. Game client is a state machine client, and this is basically what we need to interact with state machine from our wallet, from our contract monad. As you can see in the definition, it contains a state machine instance. And the state machine instance, in turn, is just a state machine and the corresponding script instance. And once we have that, this still has to be bundled with the so-called chooser. And this is the mechanism to, from the off-chain code, we need to find the UTXO that represents our state machine. So in general, there will be a list of UTXOs at the address of the state machine. And this is a function that specifies which of those, if there is more than one, which to pick. But we don't have to worry about that because we are using this NFT approach. And then this is taken care of us automatically. There's a make state machine client function that just gets a state machine instance and produces a client. And that uses the default implementation of this chooser that picks the right UTXO. And because we have specified just an asset class for the NFT, so we are using this NFT mechanism, the default implementation will do the right thing and pick the UTXO that contains the NFT. So to get the client, we first create a state machine instance. Remember that bundles a state machine with the script instance of the state machine. And we already have those parts, so we can use this game state machine prime game and the game inst game to get those two. So we have a state machine instance, and then we use the make state machine client to turn this into a client. And now the client can be used to interact with the state machine from off-chain code. First parameters are exactly the same. There's one small nuisance that these state machine contracts that the state machine module provides, they use a specific error type, or they have a specific constraint on the error type. And one error type that works is SM contract error. But I want to do what I did in the last lectures and always use text as my error type. So in order to make those two fit together, I define this map error prime function, which uses the map error we have discussed before, and it turns an SM contract error into a text by showing the SM contract error and then packing the resulting string into a text. So now the first game becomes much shorter and much more compact. So the beginning is the same. We look up our own public key hash, define the game. Now we take the client. As soon as we have the game, we can use game client to get the client. This is our stake as before. This is our choice as before. This is the hash as before. And now there's a function run initialize that starts a state machine. So it creates a UTXO at the state machine output, at the state machine address. It takes the client as its first argument. We have the client now. And then it needs the datum and the value. So that will be the initial datum and the initial value in the UTXO sitting at that address. And it will automatically put the NFT there as well. So we don't have to specify the NFT in this value. I only specify the stake that the first player puts there. So this is all that automatically submits a transaction that does this. Submits a transaction that sets up this UTXO with the initial datum and value. And I just have to scramble a bit with this map error. Or I just see that I didn't use this map error function here that I defined. So this is, I can write it much shorter now using this helper function I defined. Okay, so this is all to set it up. And now if we recall, we have to wait, and then we needed this helper function find game datum or game output in order to, after we have waited for the second player to move, to find the UTXO again. This is now much simpler because we can use something called get on-chain state. So get on-chain state takes the client and returns something of type maybe on-chain state. So if it finds the state machine, then it will return just on-chain state, and if not, then nothing. So what is on-chain state? On-chain state is a tuple consisting of typed script txout and typed script txout ref. This is similar to what this UTXO add gives us. I mean, there we always got this map from O refs to O's, from TXOut refs to TXOuts. And this is similar, so it's also basically the UTXO itself and a reference to it, but it has this typed version that we haven't seen before. And all that does is it basically bundles what we know from before, this TXOut, but additionally it provides the datum. If you recall, we always, in our off-chain code, we always had to scramble and write helper functions to access the datum once we had found a UTXO. We had to look up the datum hash, and that could fail, and then we had to look up the datum to this hash and so on. And all of this is basically hidden from us by using this TypeScript TXOut type, which we get by using this get on-chain state. So by using get on-chain state client, we have this M, and this M, it could be nothing if no output is found. As before, this should never happen, but if it does, we throw an error. And now we get this on-chain state. We are not interested in the reference, only in the O itself. And then we use this TY, TXOut data, O, to directly access the datum. So no need to look up hashes. That's all somehow wrapped in this TY, TXOut data. So now we immediately have the datum. And as before, we have the two cases, that the second player hasn't moved or that it has moved. So if it hasn't moved, we must reclaim. And earlier then we had lots of code to set up the lookups and the constraints that we need. Now we only need this line. So the important function here is run step. So run step creates a transaction and submits it that will transition the state machine. And it takes as input the client again, and then simply the redeemer. That's all. All the input we need is the redeemer. And then we will get this transition result, and I'm not using that in this example, but that basically encodes whether it failed and for what reason it failed, or whether it succeeded, and if it succeeded, what the new state is. But I don't really need this in this example. So this is all. This is really dramatically simpler. So all I have to do is I tell it, okay, in this case, the second player hasn't moved. I just do a step with the claim first redeemer. No constraints, no lookups, no submissions or waiting. This is all handled by the run step. And this is really neat, I think. This is dramatically simpler than before. And the way it works, of course, is that in the transition function, these conditions use these constraints. So all the constraints are available to the state machine mechanism, and that allows it to handle all of this automatically and to automatically assemble compose the transaction that is needed. So this is where the state machine approach really plays out. So basically it's just this one line. And in the other case where the second player has moved, and if we think we won or if we know we won, again, now we have to reveal, and it's just this one line. So again, run step client with the reveal fp nonce fp redeemer. And that's all. No constraints, no lookups, nothing. So this is much, much simpler now. And we don't need any helper functions as we did before. And same for the second player, it's just as short. So second game, the beginning is the same. We look up the public key hash. We define our game parameter. We define the state machine client. Then we use this get on-chain state again to check or find the UTXO that represents the state machine, represents the game. If we don't find it, that means no game is running. If we do find it, all these other pieces of information we could use, we don't need, only the O. And again, we use this typed version to grab the datum. And this case would mean that we haven't played yet, so now we should play. And other cases are unexpected. So we expect that we can play. And in order to play, again, it's just one line of code. We use run step and then the play our choice redeemer. Then we wait as before until the reveal deadline has passed. We again check the new state, and now if there is none, that means the first player has won, so we don't do anything. But if there is something, it means the first player hasn't won, and again just one line of code to claim our win. And that's it. So here it really shines, the state machine approach. It was already, I think, a bit shorter here in the on-chain code, a bit more concise. We needed, particularly we needed less helper functions. We didn't have to worry about this handling of the own input, own output, and of the NFT that it's passed through. But in the off-chain code, it's really dramatically simpler now and much more readable. And the rest is exactly the same. That's just copy-pasted. And what is particularly nice about the state machine approach is that we don't have to replicate logic anymore. I mean, earlier I explained that the on-chain validation checks whether a transaction is valid, whereas the off-chain code has to construct a transaction that then will pass these checks that validation does. So on-chain and off-chain logic has slightly different purposes. On-chain has to check, whereas off-chain has to construct. But by using this trick to specify the state machine using the constraints that can be used for both, for checking and for construction, we now don't have to replicate this logic anymore. So we only use the constraints, and they can be used to construct the transaction, but also to check the transaction. So in principle, we halve the amount of code we need to write, and we remove a lot of duplication. In order to test this, I created a module test state machine, and this is literally the same code as of the test module we saw before. The only line that's different is this line 28, where instead of importing even odd, I'm now importing state machine. Everything else is exactly the same. That's of course silly, and I could have done that differently, that I only have the test code once and then parameterize it over which contract I want to use. But I just did that quick and dirty. So if I load this in the REPL and run test, I should get exactly the same results as before for the 4 scenarios. So 0, 0, the first player should win, and 0, 1, second player should win, and so on. So state machines are not always appropriate, but when they are, you should definitely use them, because they dramatically reduce the amount of code you have to write, and also remove sources of error, because you avoid code duplication. Basically, the state machine automatically takes care of guaranteeing that the on-chain and the off-chain code fit together. So the off-chain code will produce transactions that then will be validated by the on-chain code. And until now, we always had to take care of that by hand. So a big source of errors or bugs is removed, and everything is much shorter, because a lot of the machinery to identify the right UTXO and to pass through the state token is taken care of for you automatically by the state machine mechanism. Of course, it's not always appropriate, but when you have this model that there's basically one specific UTXO that carries some state in its datum and that transitions, so there are transactions that consume this UTXO and produce a new one at the same address with a possibly updated datum and value, then you should definitely ask yourself whether you can model that as a state machine and then use this state machine mechanism. For homework, I recommend that you modify the state machine module and implement the rock, paper, scissors game instead of this game we implemented. And so the game definition can stay exactly the same, but then for choices, instead of 0, 1, we have 3 choices: rock, paper, and scissors. And then the implementation of equality changes, of course. So rock equals rock, paper equals paper, scissors equals scissors, nothing else equals anything else. And I suppose it will be helpful to implement a beats function that takes two of these choices and then says whether the first one beats the second. So rock beats scissors, paper beats rock, and scissors beat paper, and that's all. And I want you to re-implement the game with these additional options. So a lot is very similar. The only difference, of course, is that now there's also the possibility of a draw if both players make the same move. And in that case, of course, the stake should be split. So each player should get his or her own stake back. There's one more change you need to make to the redeemer type. Earlier in the reveal case, we only had to provide the nonce. We didn't have to provide the actual move that the first player made, because he would only reveal if he won. So if he made the same move that the second player made. So this was redundant information and we didn't need it. But now we do need it, because there are two possibilities what the first player could have done. If he knows he lost, he won't reveal. But he could reveal if he won, but also if it is a draw. Because if he doesn't reveal, even if it's a draw, then the second player would get everything. So the first player now must reveal if he won or if it was a draw. So in order to write down the correct conditions, we now need the choice that the first player made. And with that, you need one more case in the transition function to take care of this draw case. And there are some slight modifications. For example, now you need 3 of these byte strings. Instead of 0, 1, you need 3 choices for how to represent rock, paper, scissors. And also in the off-chain code, there's a slight change when you check what to do if there is a draw. But everything is very similar, so there are not a lot of changes needed.